Alright guys, second lecture, okay. The first one I said I'd do a short one, but yeah, apparently it's like 20 some minutes. And yeah, guess how large the video file is? It's close to 1 gig. So yeah, I think 20 some minutes probably the longest I'm gonna go. In this following couple of lectures, I'm gonna do a couple of examples to show you how we use this, principal virtual work, displacement function, those fancy terms to solve some simple problems. And like this example, yeah, it's really simple. You got a cantilever beam, EI and L, and then it's been pushed by a force P. We're just saying, okay, what's the deflection? You're like, come on, mechanics of material, or we can do structural theory, double integration, or whatever, or unit force method, whatever. But yeah, we're gonna do it a little bit different. We're gonna use principal virtual work. We're gonna actually, do that. So first of all, you gotta know what you're trying to get here. Here, what you're trying to get is delta, but more specifically, if you look at this x and y, what you really want to get is v of x. So basically, you want to get the deflection of this entire beam. All right. Then you're like, okay, how am I gonna get it? Immediately, if people, they remember double integration, they say, oh, okay, yeah, I got it. The Vx, when there's a couple of things here, when x equals 0, it should be 0, and because cantilever, not only the x equals 0, v 0. Also, the slope here, is 0. Okay, well that's great. So that kind of tells you this function. First of all, it should not have a constant here. So basically, you say, okay, let's not be fancy. Let's just say Vx equals to a plus bx plus cx squared plus dx third. I don't know. Yeah, maybe it's a good time to stop here. But immediately, like, this guy's gonna be 0 because it's not gonna be. Yeah, if it's not 0, you plug in x or equals 0, you got a. So which means its deflection here is a. There's no deflection here, so it's 0. Okay. Then the b is 0. Why? Because if you take derivative, a is gone, b became b, and then at x equals 0, those are 0, then b, the slope here should be 0. Okay, so we got that. Yeah, so it seems like, we could just say, it's cx squared plus dx third, which is c and d we don't know. And, you guys like to cheat? Yeah, you're like, what? Okay, well, I don't know about you, but when I'm trying to solve a problem that I'm not familiar with, I like to cheat a little bit. So I'll do a little cheat. So I will actually go to the back of one of the classic mechanics material books and find this formula. In fact, the formula is this. PL2EIX squared minus P6EIX third. So by cheating, I kind of know C should be this guy and D should be negative this guy. But this is cheating. We're not gonna do that, right? We're gonna do the normal way, principal virtual work. Okay, so to solve this, in fact, we just did the first step. The first step here for doing any principal virtual work thing is assume a displacement function. Then you're like, okay, well, we know that's the displacement in y direction. How about u? Yeah, u. I mean, if you still remember, will simply be negative y dv dx. Yeah, that's from the notes of last lecture. And then you're like, oh, how about w? Well, if you really want to write it, w equals 0. Because, come on, this is a 2D problem, okay? But we do have our 3 displacement functions, so we assumed it. There are some unknowns we don't know. You're like, why are you cheating here? Oh, the cheating here is to make sure that I know I got this term right, this term right. Yeah, it's got a second order term, it's got a third order term. So we're good. Okay. So, number 2. Remember, this is the displacement we want to solve. This displacement is real. It is the displacement under P. So to do principal virtual work, we need a virtual displacement. So you need to choose a virtual displacement. I mean, ideally, not like in general, you need to choose this, and you need to choose this. But you know what? I'm gonna kind of just follow this route and just say, hey, you know what? I'm just gonna do this. Then those will just come. And so, what are you gonna do with it? This can be any function that satisfy boundary condition. Then you're like, okay, well, you said this is arbitrary, and now you're telling me about boundary condition now. In fact, if I really want to tell you the truth, it doesn't matter. If your virtual displacement does not satisfy boundary condition, which means it's gonna like juggle and move this end, it is actually okay, but the catch is that in the external virtual work term, you have to include the external virtual work done by the reaction force. In this case, the reaction force are easy, but like who? I mean, we got enough problem to work with. Like, who want to solve for reaction forces here? So if you make your virtual displacement satisfy boundary condition, the reaction forces, they will do 0 work on your virtual displacement, so you don't need to worry about them. Okay, so that's the first thing. And then you don't have to use it, but typically we use the same format as the real displacement. But then you're like, you say they're different. Well, yes, I did so. So what we're going to do is that we say the virtual displacement function is simply virtual 1 x third plus x. Yeah, let's do that. Oh yeah, let's just do this. Virtual 1 x third plus virtual 2 x second. So I mean, not exactly, but you got 2 terms, and yeah, sure. So they're about the same. So just to be clear, is like our real displacement is dx third plus cx second. So once you get that 3, is just to apply the principle of virtual work. Yeah, you're like, okay, great, that's very nice. Like, how do you actually do it? So basically just follow the formula. So you know principal virtual work is this. 0 equals to the external virtual work minus the internal virtual work, right? So just write it out. So let's do the easy part. External virtual work. Let's take a look at the situation here. Okay. We said reaction force. You know, we don't care because our virtual displacement does have. Yeah, they don't do anything. The only external work is this external force is this P. Okay, it works on the virtual displacement at the tip. So what the virtual external work is simply P times this guy at x equals to L, right? Minus internal. Then this guy, yeah, you just plug it in. I mean, just plug it in. Okay, so it becomes P delta 1 L third plus P delta 2 L second. Delta 1, delta 2, they are just some arbitrary number of whatever. You know, it's virtual. The minus. Now, if you still remember the lecture, in fact, I actually have it from last lecture. Yeah, okay, well, remember this formula? The Euler Bernoulli beam 2D, the internal work is just this formula. So basically, EI and then do the integral of the real V second derivative times the virtual V second derivative. Oh, great. Let's do it. So you got the EI here, and and then you 0 to L, and then you need to take second derivative of this guy times take second derivative of this guy. So second derivative of this guy is like 3 coming down, then 2 coming down. So it's 6 dx plus 2c. That's a real displacement. Taking second derivative, then times now the virtual. Okay. 6. Yeah, you find this is like really pretty amazing. So this guy is actually the virtual, taking second derivative, and then dx. Okay. So we'll need to do a little work here. You notice the whole thing equals 0. Okay. And in fact, another kind of a nice way to think about it is there's a negative here, right? Yeah, we can just rewrite this by making this to be equal. So we'll have on this side P L3 times delta 1 plus P L second times delta 2. On this side we got not 4 but L. Okay. Do the time them together and do the integral. Okay. In fact, you know what? What I'm gonna do is I'm gonna take the EI over here. Okay. Just divide both sides by EI. And then I'm just gonna worry about this because I mean it's a mouthful. Okay, then this times this. So 36, 36. Then d x squared times delta 1, right? Then plus this guy times this. So it's 12 dx then delta 2. Great. Then plus then now this guy times this guy. So 12c delta 12c x times delta 1, and finally those two guys, and then 4c delta 2, 4 plus 4c delta 2. And this entire thing we need to do the integral. I don't know if you guys still kind of familiar with the integral or what, but yeah, here you go. If you do one integrals, then you take 3 from this guy and put it back here. So basically what you're gonna get is 12 d x third on delta 1. You're like, hey, what? Like delta 1 still here? Like why? Okay, we're doing integral of x. Delta 1 is just a constant. We just don't know what it is. So, you know, it just hop on the right. Then plus, then you do this. This is just take 2, so 6d x squared delta 2. This guy plus 6c x squared delta 1. And finally, plus, yeah, it's just 4c delta 2x. And then we integrate it. You know, to do the integral, you need to evaluate it in between 0 and L. And then so basically, what you do is that you put L in all the x. The minus you put 0 in all in x. But yeah, because this guy's 0, so yeah, in fact everything's 0. So it's just putting x, L in all of that. Well, gee, we need another piece of paper. So basically, you know, what we gonna end up doing is something like this. This will be equals to, and now I'm gonna like group the delta 1 and delta 2 terms. The first term is the 12d L third. And then where's another delta 1 here? Okay, here. So plus 6c L second times delta 1. Then plus, I'm running out of space here, so I'm going to write it here. Now the delta 2 guys, okay. 6d x squared. So it's like 6d L squared. Delta 2, I'm not gonna, yeah, then just plus this guy 4cl delta 2. So what are the equals? It equals to this guy. And this is like a beauty of, you know, it suddenly becomes this plus one equation, because the arbitrary nature of delta 1 delta 2 becomes 2 equations. So this is still like one equation. This guy plus this guy should be equals to this guy plus this guy. But we know that delta 1 and delta 2, they are just arbitrary numbers because they are virtual displacement terms. So what happens is that you end up with a two functions. And yeah, don't forget what we're looking for. We're looking for D and C. 2 equations, 2 unknowns. Gee, yeah, looks like we could solve for C and D. So in fact, this is the beauty part. Yeah, you just rewrite it and then it becomes PL3 EI PL2 EI equals to yeah, you're gonna love this. 12L third and 6L square then 6L square and 4L. not C, and then times D and C. Gee, you know, you're taking matrix structural analysis. I mean, at this point, you should be very, very clear. These are actually just two linear equations, and the only unknown here is D and C, so you can actually solve for that. Then you're like, how am I gonna do that? I mean, yeah, if you have a number in L or EI, you plug in numbers, and you can use MATLAB to solve it. But you know, MATLAB can also do symbolic operation. But anyway, the long story short, if you solve it, and you can kind of plug it back in to see if it works, you will find out actually what happens is that yeah, where's my notes? Okay, what happens is that yeah, you know what? Let's just solve it by hand, okay? So that you know we're doing this. Let's say PL3. Let's rewrite it. There's gonna be a lot of paper. Okay, 12A L third plus 6B L second. Let's call this not doing this. D C. Okay. And then let's call this equation number 1. And then we have this PL second, EI equals to 6DL second plus 4CL. Let's call this equation number 2. You can do it by yourself, okay? I'm not saying you cannot. So you take number 2, you time both sides by 2L, then you minus number 1. What happens is that you see this term, if you times 2L, it becomes exactly this guy. Then you do the minus thing, it'll get rid of D, okay? So once you did that, you do it by yourself. C, it happens to be PL over 2EI. And then once you get that, you substitute that into number 2, and then you find out your D equals to negative P over 6EI. Okay, just do it yourself, okay? I'm not like kidding with you. Then you plug it back in, and then number 5, the step 5 is finally, you say, hey, didn't I assume this to be cx squared plus dx third? Hey, look at it. It is actually exactly like my, I'm not going to do that. Exactly my, my standard answer. Negative P over 6EI and PL over 2EI. Don't believe it? Here. Okay. You're like, yeah. So basically this is how we use principal virtual work to solve for the, you're like, oh, okay, you didn't solve for delta. Oh, well, I solved for the entire thing, okay? If you want delta, you just plug a, L in there, you get delta, okay? If you want to like half span, you plug this L over 2 here, yeah, that's how it works. But then there's somebody's kind of clever. Say, okay, well, you did this all because you initially cheated and did this, and then I think that's the foundation. I mean, you know it's x to the second power, x to the third power. What if you don't know that? Well, this thing still works. A short answer is yes, and then we're going to show you that in the next video. Yeah, principal virtual work is really pretty amazing if you ask me. Alright, See you next time.